How far into the future can the things around you actually count? Your phone is counting seconds. So is your television, the watch on your wrist, and the router in the hallway. They are all counting the same thing. Seconds since midnight on the 1st of January 1970. The number is the same everywhere. How far it can go depends on the size of the counter holding it, and a 32-bit counter runs out at just over 2.1 billion seconds. 2.1 billion seconds is about 68 years. Add 68 years to 1970 and you arrive at January 19, 2038. That is how far a 32-bit counter goes, and early that morning it reaches its last number. Some of those things are still counting in 32 bits, and Google says so about its own. Android phones were moved onto 64-bit code years ago. Televisions and watches running Android are still being served 32-bit code 7 years after the phones. Google's documentation is blunt about what that means. On 32-bit Android, the clock overflows in 2038. On 64 bits, the same page says, it will not overflow until long after the death of the star around which we currently circle. Your phone and your laptop were sorted out years ago, moved on to the wider count. The things that sit in one place for a decade often were not. One of these devices has already been written up. Last October, an American government advisory went out about an automatic tank gauge, the console that watches the fuel tanks under a filling station. When the count runs out, its clock drops to 1901, the staff are locked out, and it stops checking for leaks. The count has had 3 deadlines. 2038 is the third. The first was set for the spring of 1973, and this is how the world ended up running on the third. November 1971. Bell Labs prints the manual for a brand new operating system called Unix, and the page describing its clock carries a section headed Bugs. The note is a death notice addressed to the chronological-minded user. The clock it describes can only hold about 2¼ years of time, start to finish. That first deadline is printed on that page. The clock had started counting 10 months before it went to press, on January 1st, 1971, which left it about 17 months to live. The clock in question lives in a PDP-11, the mini-computer early Unix ran on, and it tells time by counting the electricity coming out of the wall. American wall current alternates 60 times a second, and every cycle taps the processor once. So the date, on this machine, is the number of times the power feeding Bell Labs has pulsed since New Year's Day, a clock made of grid flicker. The trouble is arithmetic. At 60 ticks a second, a 32-bit counter fills in about 2¼ years, and then it cannot go higher. The manual is honest about how little that is. The system call is not named getDateAndTime, it is named getTimeOfYear, because a year is roughly what it could promise. A companion page owns up to a second bug in the date code. Yon1 comes out Dec32. The rescue was not a fix. By March 1972, the manual's page for the clock had been rewritten, and time now began at midnight on January 1, 1972. Nothing about the counter changed. The beginning of time had simply been moved forward a year, and deadline number 1 became deadline number 2, 1 year further out, the same crisis, rescheduled. The manual did not pretend otherwise. Its BUES section now reads, in full, the time is stored in 32 bits. This guarantees a crisis every 2 to 6 years. That was the operating plan, a standing appointment with the end of time, renewed by hand. The real fix arrived by 1973, before either deadline could land, and it is almost anticlimactic. Stop counting 60ths. Count whole seconds. Seconds are 60 times coarser, so the same 32 bits now reached about 68 years into the future instead of 2. And the 0 moved one last time, backwards, to a date nobody ever moved again. Midnight, January 1st, 1970, Greenwich time. Every Unix-descended computer on Earth still counts from that midnight. A new edition of the manual, published in November 1973, renames the call getDateAndTime. For the first time in its life, the clock could hold a date. And the bug section is gone. Not fixed, removed. At 68 years range, the crisis no longer qualified as a bug, and the warning that had shipped with this clock from the beginning disappeared. Just over 2.1 billion seconds past that third 0 sits the third deadline, January 19, 2038. 68 years and not more because of one detail, the counter is signed. Its first bit does not count seconds, it records whether the number is positive or negative, so that moments before the 0 can exist at all. At its maximum, the counter reads as a single 0 followed by 31 ones. That value is reached at 14 minutes and 7 seconds past 3 in the morning, UTC, on Tuesday, January 19, 2038. 1 second later, the machine adds 1, and the carry ripples all the way up into the sign bit. The counter flips to the most negative number it can hold, 2.1 billion seconds before 1970. On a calendar, that is the evening of December 13th, 1901, which was a Friday. An unpatched machine that follows the arithmetic wakes up on Friday the 13th, 137 years in its own past. It is the date the tank gauge falls back to. Real machines vary at that tick. Some crash, some freeze at the ceiling, some display 1970. 1901 is simply what the raw arithmetic says. The deadline spent its first 3 decades as a curiosity. In September 2001, Unix time approached 1 billion seconds, and its users planned celebrations for the odometer moment, fireworks at a Copenhagen conference among them. That week, Wired asked Dennis Ritchie, one of the 2 men who built Unix, where the 0 had come from. He had been in the room when it was picked, and he turned 60 that very weekend. What he remembered was housekeeping. There were no tape backups then, just a couple of young file systems, so moving the beginning of time broke almost nothing. We kept changing the origin of time. So finally we said, let's pick one thing that's not going to overflow for a while. 1970 seemed to be as good as any. So the 0 at the bottom of the digital world is not a monument to anything. It was the 3rd try, chosen to buy time, and Ritchie said so in print. The same interview turned to 2038. Ritchie was untroubled, sort of like a Y2K thing, he said, but it's less serious. The new 64-bit processors, he added, will last millennia. A lot of millennia. The first crack in less serious showed 5 years later on a spring weekend, 32 years ahead of schedule. In May 2006, web servers running a system called AOLserver began hanging, and their administrators spent days chasing what looked like a memory leak. The real cause was a number somebody had chosen years before. An old database driver had a timeout bug, and the recommended workaround was to set the timeout so large it meant never. The value chosen for never was 1 billion seconds. That is about 3 decades. On the project's mailing list, Boss Sheffers did the subtraction. The servers had started dying in the small hours of May 13th, exactly 1 billion seconds before the count ran out. He asked, coincidence? It was not. Those machines had been looking 3 decades into the future every time they opened a connection, and that morning what they saw crossed January 19, 2038. The timeout wrapped negative and the software fell over. Another member of the list, Jeff Rogers, spent a day tracing it and reported back, I've been enjoying telling people that I hit my first Y2038 bug. 2038, it turns out, is not a wall sitting in the future. It is a horizon, and any software that lives far enough ahead crosses it early. Systems that live decades ahead have been hitting it since 2006. Ritchie's 64-bit processors did arrive. They did not end the problem, because the problem was never the processor. What a processor can compute and what a file records are different things. The count that runs out is a format. It sits in file systems on disk, in database columns, in network protocols, in code that says integer and means 32. A 64-bit count of seconds is effectively bottomless. It runs for about 292 billion years. Moving the world onto it is the hard part, and the edit has to reach everything. In 2014, the warning that came off the manual page in 1973 finally became somebody's job. A Linux kernel engineer named Arnd Bergmann took it on. More than 1,000 files in the kernel used the old 32-bit time. The aim was to finish inside the year, and it took until 2020. In January 2020, he sent in the closing pull request. Kernel 5.6, it says, should be. The first release that a 32-bit system can build on and run past 2038. Should be, provided every program sitting on top of the kernel gets rebuilt with the new time as well. Rebuilt is the expensive word. Debian is a Linux distribution assembled from tens of thousands of separate programs. It is what full scale looks like. When a timestamp changes size, every library that passes timestamps to its neighbors changes shape, and the programs built against them stop fitting together. You cannot patch across that. You take the whole archive apart and put it back together. On February 2, 2024, a Debian engineer named Steve Langesek started doing exactly that, 1,200 libraries renamed and re-uploaded. He signed the announcement off. Exciting times. Debian 13 shipped the finished work in August 2025. 64-bit time on every official architecture except one, the old 32-bit PC platform. Langesek had been a Debian developer since 2001, and he was one of the transition's chief architects. He died on New Year's Day, 2025, at 45 after several years of illness. He did not see it ship. So, is it fixed? The most honest answer comes from the people who moved their clocks forward to find out. In January 2026, the community behind the openSUSE Linux distribution set their machine's clocks past 2038, rebuilt the whole distribution, and published whatever broke. Things broke. Mercurial, a version control tool, refused the dates outright with the message "date exceeds 32 bits," and an April status report summed up what the builds could not see: there are still plenty of year 2038 problems that don't break the build. In 2025, the problem picked up a sharper name: vulnerability. Trey Darley and Pedro Umbalino, two security researchers, argue that nobody has to wait for 2038. Feed a machine a false time, they say, a spoofed satellite signal or a crafted file, and the rollover happens today. The gauge under the filling station has company. A second tank gauge, from a different manufacturer, has an advisory of its own. Umbalino's estimate of the scale is a challenge that completely eclipses Y2K, with likely 1,000 times more connected systems than back then. 2038 has already started arriving in pieces. As this episode is written, the third deadline is 11.5 years away, and it is still being installed. MySQL, one of the world's most widely deployed open-source databases, still documents its timestamp column as ending on January 19, 2038. The manual's suggested workaround is a different column type, datame, which does not have the problem. MariaDB, which split off from MySQL, went the other way. In 2024, on its 64-bit builds, it began reading the same 32 bits as unsigned, surrendering every date before 1970 to buy 68 more years. Its new ceiling is the year 2106. Widening the counter only reschedules the ending: 2 years, then 68, then 292 billion. But under every clock you own there is still a counter, a zero somebody picked because it was convenient, and a ceiling filed under later. The sentence Ritchie remembered, "Let's pick one thing that's not going to overflow for a while," has been the arrangement ever since. The while is not over, it got longer. Consider liking and subscribing for more load-bearing history videos.